Heat exchangers are devices used to promote heat transfer between two or more fluid streams without fluid mixing between the flow streams. They are some of the most common heat transfer equipment and are used in many process industries and in various other types of equipment. So, oftentimes when looking at heat exchangers, they're classified in different ways. Shell and tube heat exchangers, shown here, are often used in the process industry. You might see inside, for example, baffles that allow turbulent mixing within the heat exchanger. There's said to be a shell type flow and a tube flow. So one flow would go within these tubes. You see the tubes here. Other flow would go in the shell, and we'll talk about some of the details of that. You can have refrigeration type mixtures in this brazed plate heat exchanger, or you can have compact heat exchangers, which might be shown and depicted by this aluminum heat exchanger in the right side. Common to all these different types of heat exchangers are some sort of basic analysis technique, and we'll discuss how to analyze these systems using a relatively simple model. So, just considering the two-stream heat exchanger, typically these are classified either as a counterflow heat exchanger or a co-flow heat exchanger. So in the counterflow heat exchanger, the flow is opposite in direction. And here we show a counterflow system, and we might think about it in a more abstract sense as an inner flow that's going left to right, and an outer or shell type flow going right to left. So this is a typical counterflow exchanger system. The temperature distribution in a counterflow exchanger is going to be very different from a co-flow exchanger, and what we want to know oftentimes is how the temperatures change with downstream distance. For a condenser system, this is really neither a counterflow or a co-flow. We might have steam coming in and condensate going out, and this might be a simplification of a problem because that phase change process allows us to have a constant temperature on the shell side. So you might think about the flow inside as the tube flow and the flow outside as the shell flow. And we'll see how analysis of these types of processes allows us to get heat transfer rates and temperatures. So in a typical counterflow heat exchanger, the temperature profiles are shown here. We have a hot fluid, the oil, going from some TH in to TH out. And so this is, in our particular problem, this is shown as the tube flow. And we have water, cooling water, on the shell side. So we have shell side cooling water, and tube side hot oil. So for a problem of this type, there are constraints on the shape of these curves, and I'd like you to think a little bit about what these constraints might be. So questions might be, can the cold side fluid exit at a temperature higher than the inlet temperature of the hot fluid. So that is a crossing issue. Can the temperature distributions cross? Here we see that the cold side fluid is actually exiting at a temperature that is larger than the hot side outlet temperature, and that's a reasonable thing. We'll see that the constraints on the temperature profile, that is the convexity or concavity of these, is dependent on whether these are counterflow, co-flow, and what we understand about the temperature differences. We'll also look at what it means to have curvature in these profiles as compared to having straight line, constant temperature changes with respect to X. So in this condenser heat exchanger, one of the things that you notice is that you have this exponential increase. Well, I guess at this point we don't really understand that it's an exponential increase, but we have an exponential increase in the temperature of the water in terms of its increase compared to this saturated process. This is a problem in which we have a saturated system So imagine that we have steam on the shell side and we have cold water entering on the tube side, and that cold water is increasing in temperature as it flows through. And so the question is, how does TH remain constant at a constant temperature? And we understand that in the two-phase region, thermodynamically, all the energy in the steam is being converted as the steam loses energy, that is the hot side fluid, and we form liquid water by this phase change process. So there's a rate of conversion of water vapor to liquid water, and that rate of formation, if you want to think about it as some creation rate of liquid water, and you might think about this as some m dot of liquid water times the heat of vaporization is the energy that is supplied to the cold water stream. So whenever we have a saturated or phase change process, that's actually a relatively simple case to analyze because we know what's happening in terms of temperature for that phase change system. So typically in the analysis of a condenser or any type of heat exchanger, we have to think about the heat transfer processes happening on the cold side in terms of the heat transfer coefficient or resistance and the temperature, and then what happens on the hot side in terms of the heat transfer coefficient and the temperature. Often we also have to think about what the resistance is through the material. So this is the heat exchanger walls. The heat transfer rate through the heat exchanger walls can sometimes be modified and increased because of fouling. So fouling is the buildup of mineral deposits on the heat exchanger walls, and this fouling tends to increase the overall resistance, the conductive resistance associated with transfer through the heat exchanger itself. So that's a word that we want to think about. From the perspective of a resistance analogy for a plain wall, we understand that the heat transfer resistances would be a convective resistance, in this case on the hot side. A conductive resistance for a plain wall is L over Ka, where A is the area, and another convective resistance on the cold side fluid. We know that the heat transfer rates are the same in some sense between all these walls for a steady problem. So we can think about the temperature differences divided by the individual resistances would be the total heat transfer rate through that. And that's useful, of course, because it tells us that we can look at a total resistance across the system and think about that in terms of the total potential drop across from the cold to the hot side. When we're looking at pipes and cylinders, the resistance compared to the plane wall that we looked at is ln r0, which is the radius, the outer radius divided by the inner radius over 2 pi k. This resistance that we're looking at here is r prime, and r prime is the resistance per unit length. So all we're saying is that R prime is equal to the convective resistance on the cold or the inner part of the cylinder, the conductive resistance through the pipe, and the outer convective resistance. So when we look at heat exchanger systems, one of the things that we want to do is we want to understand the energy balances in these systems. And in terms of these energy balances, there are two types of energy balances that are meaningful. One of them is a global balance, in which case we look at the overall control volume that encompasses the entire heat exchanger system. So this dashed line represents the control boundary, the control surface around this control volume. And we do an energy balance across it, and we look at the total amount of energy that comes in and the total amount of energy that goes out. So in this particular problem, as we look at this, we understand that globally the amount of heat transfer that comes in at x is equal to 0 is the flow rate of the hot fluid, flow rate of the cold fluid times the enthalpies of the cold and hot fluid, and the stuff that comes out is the flow rates at the exit. And again, it's just m dot h out, m dot c out. Rather than x equals 0 and x is equal to L, because this is neither a co-flow or counterflow, we just might say in and out. So if we pull our ins, we have m dot h times the enthalpy difference between the hot fluid in and hot fluid out is equal to the change in enthalpy flow rate of the cold fluid between its out and its in. And we understand globally that this is equal to the transfer process that goes between those two systems, between those two flows. So Q dot is the heat transfer rate between the hot fluid hot and cold fluids. If we convert to enthalpy, saying that delta H, so let's just do it in a couple steps actually. It says that dH is equal to Cp dt, or in an integrated sense, delta H, the change in enthalpy, is equal to Cp delta T. So doing that, the change in enthalpy can be thought of as a change in temperature in both cases. So we see that globally, if we know what the temperatures going in of the stream and the temperature going out, and we also know the mass flow rate and the heat capacity, we know what the heat transfer rate would have been, how much heat we would have lost to the other fluid. If we know either one of these temperatures for the other fluid with its flow rate, then we know the other temperature. The local energy balance sets up a differential equation that, upon integration, gives us the global energy balance. And so for the local energy balance, we're operating with a control volume that is delta X in length. And so for that control volume, similar issues. We have our enthalpy flow in already converted to temperatures, enthalpy flow out already converted to temperature, and we have a heat transfer rate, a differential heat transfer rate that's dependent on our overall heat transfer conductance, this U parameter or overall heat transfer coefficient, whichever way you want to think about it, the surface area, which is the perimeter times delta X, so P delta X is the surface area, where of course P is the perimeter, so we're working in a tube or pipe system, and TH minus TC is the overall temperature difference across. So just using our energy in, energy out type formulation, our energy in is the convective transfer, Newton's law of cooling, plus the convected bulk transfer of enthalpy in through the control surface at location X. And the energy out, or the rate of energy out, is the stuff that flows out at X plus delta X. So dividing by delta X, and using the definition of a derivative, or taking the limit as delta X goes to 0, we get this very simple differential equation, first order differential equation for the change in temperature of that cold fluid inside that tube as a function of X. So it says that the change in the temperature with respect to X minus this overall heat transfer coefficient times the perimeter divided by the mass flow rate times the specific heat capacity, completely multiplied by the change in temperature between the hot side fluid and the cold side fluid, is equal to 0. So that's the important differential equation for this problem. And for the simple case where it's a condensing fluid on the outside, we know that TH is equal to a constant. So this is the condensing steam on the shell side. And this is a really simple case, because if TH is a constant and it's this Tsat, then there's only one differential equation, that is that cold side fluid. And what we do is to solve this, we need we think about it as a boundary condition. You can think about it as sort of like an initial condition, since this is a first order differential equation. And so we know that at X is equal to 0, the cold fluid comes in at some temperature Tc in. We define an excess temperature, Tc minus Tsat. In terms of that excess temperature theta, it's much simpler. It looks like a homogeneous differential equation, d theta dx plus up over m dot cold Cp times this excess temperature is equal to 0. Very simple to integrate this. We just separate it. And so you should know how to separate a problem like this. We're simply we take the minus up over m dot c theta to the right side, divide by theta, and multiply by dx. We integrate, we get log theta from theta in to theta is equal to minus upx over m dot c from x is equal to 0 to some value of x. We take the inverse of this log, which is the exponential, and we get the solution in terms of this exponential of minus up m dot cp times x. When we take it back from the excess temperature to the true temperature, we just get this simple relationship for Tc. So we understand what the solution means, and the solution is relatively straightforward. It says that Tc approaches Tsat, or that hot temperature, as the length of that heat exchanger gets very large, or as the heat transfer rate gets very large, or as the flow rate gets small. So as you take a look at this argument of the exponential, and you see that as that thing gets increasingly large, that T goes to Tsat, because this exponential e to the minus of this stuff goes to 0, and T goes to Tsat. So these are the things that allow us to drive the temperature closer and closer to the hot temperature.